Okay. Questions from last time? Okay, so let's pick up where our hero left off. Remember, we're talking about these properties that an extension of rings may have. So I'll abbreviate this. Lying over, right? And so my picture is, if you have a prime ideal at the R level, there exists a Q at the T level such that Q intersect R is equal to P, right? That's the line over. You got somebody down there, there's something above it that lies over it that intersects down to it, right? We have going up. And this is when we build the next rung on the ladder. When we have P0 inside P1, two prime ideals are at the T level, O. And we also have Q0 lying over this. So we can sit down here. Going up allows us to build a Q1 that intersects down to P1. We went up. Going down, it's just sort of the reverse. We build the rungs down instead of up. At the R level, and now we have a prime ideal that lies over the big one. We can build the ladder down. Going down. And then we have ink. The extension is incomparable is if P0, I'm sorry, if Q0 and Q1 and T are primes and Q0 intersect R is Q1 intersect R, then that is, if two distinct primes lie over the same prime down below, then they have to be incomparable. Okay, so last time we proved this, and I promise we prove this one this time. Okay, so what happens here? So let's suppose. So what we know is we've got ink, right? So that's in our toolbox. We've got ink, and we've got to show that this crazy property happened, right? S is R minus P. Right. Suppose P is prime and is maximal with respect to the exclusion of S. Right. Now, of course, what we're going for is we want to show that Q intersect R is P, right? That's really what we want here. Right. So We know this, it's maximal with respect to the exclusion of S. So what can we do here? We want to show that, the intersection is exactly B. We've got going up, right? Anybody want to catch the mistake there? There's a mistake on the board. I'll give you a Hershey's Kiss if you tell me what it is.
Well, maybe I'm just don't understand what you have written here, but we're trying to show that it's maximal with respect to this exclusion, right? We're not assuming this.
Well, so what, there's a mistake up here, I think. We have, going up holes, right, then. Right. So here's where we're going here. So we've got going up and we want to show, this property is true. So I've got P and R is prime, S is the complement, and, Q is maximal with respect to the exclusion of S. We need to show that the intersection downstairs is exactly P. Oh. Here's what's wrong. I'm proving 2, not 3. Let me stretch that out. Using this property, that's my mistake. So we proved going up last time. Now we have ink, and we want to show if P and R is, we want to show this property. So suppose that P and R is prime. And Q and T is prime. Such that Q intersect R is P. So we're trying to show that P and R, if you've got P and R as prime and you've got some Q that lies over it, that Q is maximal with respect to the exclusion of S. Right? So our goal at this point need to show Q is maximal with respect to exclusion of S. Okay, everybody on board after that gap? So what can we do maybe?
You can consider a probability of T that contains Q.
Okay, good idea. So let's suppose suppose we have Q inside of Q1, right? Right. So suppose we have a prime big Q1 that is, also excludes S. What can you say about
Intersection is Q.
Q1 intersect R? What can we say about it? We're not said that.
It should contain P, since Q1 contains Q, but nothing else because the intersection with S is the empty set. So it's just
Right. My feeble brain doesn't work that quickly, so I'm gonna do this. Let me first state that. Why does that have to hold? What do we know about Q1? It excludes S, right? So that means when you intersect it down below, it has to miss S, which means it has to be contained in P. Everybody okay with that? And we in fact get equality because Q intersect R is equal to P. Therefore, the way of Q is equal to Q1. Everybody okay with that? The other way is easier, I think. Let's do the other direction. Now we've got all this yin yang here. Why is it true that we've got ink? So from that perspective, let's do this. Let Q0, comma, P1 and P primes. They contract to the prime P1. Let's assume that we have those two primes here. But this really gives it away, doesn't it? This condition here, because what happens here, you have Q0 contracts to P and Q1 contracts to P, but any Q that contracts to P is maximal with respect to excluding S. Q0 and Q1 are maximal with respect to excluding S. So one of two things has to happen. Or are incomparable. They're either the same or they can't be comparable because they both have to be maximal with respect to excluding S. Okay, any questions on that? Okay, so let me give you a big theorem that I promised. Kind of justify what this is about. This is this theorem is the machinery behind why integrality is important. And it's actually a big machine behind number theory, right? In the structure of Dedekind domains, we will talk about. This is very important because this gives light to integrality, preserves dimension. Theorem. Theorem something 515. Let R inside of P be rings. Then put it this way, if P is integral over R, then the extension R inside T, that extension, I'll talk about the extension in the singular, so if you didn't know this is an English class. This extension is both going up and ink, and it's also lying over, right? Because one of the theories we had last time was any extension that's going up is lying over. Everybody okay with that? This is a fun one to prove, so let's do this. Okay, so we're gonna reuse the characterization here that we just kind of in the previous theorems developed. Or So I want to show the interval extensions going up. We use previous notation. So here's our goal. Here's our strategy in this proof. We need to show that if P is a prime, right. We use our characterization of going up that P and R is prime, and Q is a prime ideal maximal with respect to exclusion. Of R minus P, then it contracts down to P. So this is the road we're going to take to going up. We're going to show this here. So suppose I walk up to you on the street and give you a prime P, and you find a prime Q that lies over it, or you have that situation. Whoops. Suppose we have Q and T. It is certainly proved now Q, remember, was created by being maximal with respect to the exclusion of P. It's certainly true that this is contained in P, right? This is the same kind of argument that we did before, because Q excludes S, and so when I contract it to R, it has to be inside P. So let's suppose if equality is none. Right, and we've got going up if we've got equality. Everybody okay with that? So if not, then right. There exists some X that lives in P. Right, so in other words, P is too big. This contracts down to something smaller than P. So I pick an X that's in this P here. Now here's kind of a cute little trick here. Any ideas on where we might go from here? So now that I've isolated the cell together.
We can take the idea generated by Q and X, but we need to show that the thing doesn't intersect with S, right?
Okay, that's exactly the right track. In T, this ideal must strictly contain Q. Because after all, if X is in Q, then it would be in Q intersect R, right? And so since it strictly contains this, it must hit S, as you point out. Okay, this is where I get my hands dirtier. by writing down something. Here we have something in S, it's also in here, so, there's this S and S, such that S is equal to, AS plus Q. Let's say, where A is an element of the ring and Q is an element of the ideal. Right.
A is in Q, right?
Q is in Q, right? And what was the question about A?
A is in T, right? But we're taking the ideal generated in T.
That is correct. Right, that's a good observation. A is in T because it could be generated by something other than T, right? Now, what I do know is that, what I want to do is I want to write the equation for integrality of A. Here's where I use the integral extension, right? So I don't know much, but I do know that there's some integral extension. So let me write this down somehow. This is AN plus RN minus one, AN minus one, R1A plus R0 is 0, with all the RI's of the interval. Now, I'm gonna bootstrap that by making, in fact, an equation, an integral equation for AX. I'm gonna multiply, both sides by X to the N. And let me write this out here. Right? And everybody agree with my algebra there? Everything okay? Okay, so now I've got an integral equation for AX, right? No shocker there, because AX is still on T. What can I do now? Okay, I'm gonna take some algebra liberties here. I'm gonna do this one. I'm gonna replace AX with S minus Q. What I'm gonna do, I'm fumbling toward getting a contradiction about this multiplicative set. X. Right. Now, what I'm gonna do is I am just going to be like a surgeon. Sorry, that's a typo. That one should be an S. I got the other correct, didn't I? I'm gonna be like a surgeon and I'm gonna remove the leading term, right? Leading term of this is S to the N. Leading term of this S to the N minus one. Leading term of this has a factor of S in it. So I'm gonna rewrite this equation as follows. Sn plus Rn minus one, S to N minus one. Right, plus, oh, and there probably should be an X there. Yeah, there's an X. R1 X to the N. S.
Sorry.
Now,
That coefficient should be R1 X to the N minus one, right?
It should be, yeah, thank you. And to show you what a lazy man I am. Right. Uh, Let me put a hat on this. It's not the same here. What did I do with my magical mathematical prestidigitation? Is I excised the first term that came out of the powers of this, and that's where that first chunk comes from, including this bit. Notice every stinking other term has a factor of Q in it, right? The original Q. Agreed? So that shoves this. So being lazy, I just say, okay, this is Q. And where does this Q with a hat on it live? Correct. This is in Q. And where else does it live? R. It also lives in R. Because of this side of the equation, right? Because all the players over here, S, R, and X, are all elements of R. So this is actually in Q intersect R, right? Which is in P. So let's examine this part of it. This is an element of P as well, right? Because X is, or I'm sorry, not an element of P, but that element of this larger prime. And so Sn is not in S because it has to be in this prime here, which is really kind of cool because we excise all that and we took advantage of the fact that this is a multiplicative set. So that gives if we have integrality we've got going up. The ink is a little bit easier, I think. For ink, again, I'm going to use the previous notation. So in particular, what I want to do here is I want to show. So I'm going to take this characterization of ink that we had. I want to show that if P is a prime and Q contracts to it, Q P contracts to P, then Q is maximal with respect to convincing S. Okay, so that's where I want to go with that right there. And this one's quicker, but it's a clever argument. So you might want to kind of check this out. Assume that P is contracted for Q, and again, we're trying to show that Q is maximal with respect to missing the complement of P and R. Q is not maximal with respect do Q intersect S. Then there exists an ideal I strictly containing Q such that I intersect S is empty. There has to be some slightly bigger ideal that contains Q and this is S. And of course, we can expand I to a prime. And I could pretend that I is prime if I want, but here, I don't care. I just really think that there's a proper ideal that contains it. Okay, so what I'm gonna do is pick out some U that lives in I, but is not in Q. I can find a polynomial, again, I'm using integrality here. Well, let me write down the polynomial relation and then we'll kind of pick it apart. Among all polynomial relations, we find f, let me say polynomials, that's a better way to put this. Among all polynomials, we find f of x minimal with respect to degree such that f of x and rx, I'll make that clear, and f of u is in Q. We want that in Q, don't we? Okay, and let me write this down, but then I wanna go back to take a quick critical look at this here. So say it is say that this is a minimal degree. So, okay, now, how do I know that such a polynomial exists?
At least one, I don't know, close to zero.
Well, right, so what did you say?
There's 1, 0.
There's one that's zero, right? And this, again, this depends on the fact that this is an integral extension, right? So I know that out there in the depths of some Stephen King novel, there is some polynomial in Rx such that f of u is zero, right? This is a looser requirement, isn't it? Because zero is in every prime ideal. So certainly there might be some smaller degree polynomial where f of u is in Q. So let's suppose that we have this polynomial relation and it's minimal with respect to n, right? So notice that the constant term notice that R0 must be an I, right? Because each power of u is in I, and the result is in Q, so R0 at the very least has to be an I, and of course it's in R as well, right? By hypothesis, and I intersect R is contained in P, which is of course contained in Q. Now, check this out. This product is now Q. But neither term is. Let me say instead of term, let me say factor. Neither factor is. U is not in there by hypothesis, and this mess isn't by minimality, right? And so there's our contradiction. And so we get the coveted result that any integral extension satisfies both lying over and inc. Okay. Why do we care? What is important about lying over and inc? Well, both lying over and inc tell us something very important about Krull dimension, about how high we can stack the prime ideals. So let me give you kind of these dual lemmas here. Lemma 519. If R inside of T is going up, then the dimension of R is less than or equal to the dimension of T. Okay, why is this true? Why is this true? Let's let suppose we have a chain of primes that link in like this. What does going up allow us to do? Well, the extension is going up, so it's lying over, so we're using that corollary. So I'm gonna be sloppy enough, hopefully you all can get the idea here. Or we could even take it at the R level. Okay, the extension is going up, so it's lying over. So lying over gives me my C, right? So Q0 lies over P0, but the extension is going up. So I can now build Q1 that lies over P1, but the extension is going up. So now I can build Q2 that lies over Q3 all the way up Qn, lying over Pn at the T level. Translation. There exists a chain of length at least n and T. So I've got dimension covered this way. Everybody okay with that? You could probably smell the next one coming. Lemma 5110. If R inside T is inc, then now the dimension of the bottom is at least as big as the dimension of the top. And again, I'll just kind of give you a brief why is this true. Suppose there exists a chain of length n and T. So suppose we have Q0, Q1, Q2, Qn. Suppose these are strictly increasing primes. Intersect it. And I don't know much, but when I intersect down to the R level, I'm gonna get primes, and they will be I certainly intersecting down here, I get a chain here of n primes, but why do I get to put the magical little not equal to in here? Why do I get to go like that?
The extension that's incomparable.
That's right, ink is set up to help that stupid stuff from happening. Because what happens is this contracts to this, and this one cannot contract to this because of ink. So this one has to contract to something that strictly contains this. This one contracts here, this one can't contract to here because of ink, and so forth and so on. So we've got sort of the dual notion of what we have here. There exists a chain of at least, of length at least N and R. And there you go. Any questions on that?
Any inter extension of rings, maintain the dimension, right?
That is correct. So that is, so Pedro got the punchline. That's exactly right. So this is the last theorem in the section that ties this together. So I'll call this something theorem 5.1.11. If R inside P is GU and ink. So in particular, if P is integral over R, then I couldn't do that because then you'll think that's dimensional T factorial. That would mess up your computations. But this is a super, super powerful theorem. Let me give you a quick, yes, sir.
So one question, so, U and ink doesn't imply interal necessarily, right?
I'm sorry.
U and ink doesn't imply that the extension is interal necessarily.
Oh, right. That's a good point. Yes, you can have extensions that have both of these properties that are not necessarily integral. Right. But integrality is a great thing. So in fact, if you remember me talking about, well, so there are some generalizations of integrality that I've worked with in my own research where, and I can't even remember right now, I think one of the generalizations loses ink, but it keeps going up, for example. Here's an example. This is the very famous this is famously called the ring of all algebraic integers. So it's a set of all complex numbers as the root of some monic polynomial, coefficients in Z. So for example, in there you have I square root of -2, all 5 complex roots of x to the 5 plus 2x plus 6, all kinds of crazy stuff. This is formed. This is the algebraic closure of Q. It's a bar. Then Z bar is formed by taking integral closure. This previous theorem says that this thing has to be dimension 1, just like the integers, which is fantastic. And it's really cool because it's highly ink, because over any non-zero prime in Z, pick your favorite prime, 2, 8, 6, 7, 5, 3, or 9, whatever you like, there will be infinitely many prime ideals that lie over it, and they're all incomparable, as a matter of fact. Okay. Any questions on that? Okay, so this leads up to an incredibly important topic. We have talked about proof of domains, and now we're going to talk about proof of domains, more famous relative Dedekind domains. And how do I define it? Actually, and I'm not being facetious here because I really want to see how I define it, my word, because there's something like 50 or more actually characterizations of Dedekind domains. Literature, which one did I use? Oh, that's a good one. Definition. An informal domain is a Dedekind domain if all, well, non-zero ideals of R are invertible. So you can see that this ties in with proofer, right? One of our definitions, one of our equivalent conditions for being a proofer domain is, well, does anybody remember what seems to relate to this most? Right. Proofer domains means all finitely generated ideals of the domain are invertible. This sucker says every ideal, finitely generated or not, is invertible. So what's the first observation I can make about any Dedekind domain? Given this, that is correct. Any Dedekind domain, given this definition, must be Noetherian. Because if every non-zero ideal is invertible, we know that invertible ideals must be finitely generated. So this sucker is always Noetherian. So let me give you some of my favorite, these are some of my favorite things here. And this might be a good place to, yeah, I've got just enough time to do this. So theorem. Like I said, there are an Avogadro's number of equivalent conditions of Dedekind domains in literature. Let me give you some of my personal favorites. This is Jim's hit list. R, a domain. The following are equivalent. Number one, R is Dedekind. That is to say every ideal, non-zero ideal is invertible. Number two, R is Noetherian. I like this one. Infinitely closed. And the Krull dimension of R is less than or equal to 1. If the Krull dimension of R is 0, that means it's a field, right, which is the world's most boring Dedekind domain. Number 3, R is Noetherian. And R localized P is a Noetherian validation domain. For all prime ideals. You may wonder if the second statement is enough, but it's not. You need to also assume the R is Noetherian. And number 4, every non-zero ideal in R is a product, uniquely in fact, of prime elements. This one ties it in with UFDs. So a Dedekind domain is sort of like the poor person's UFD. You can't necessarily factor the elements uniquely into primes, but you can take every non-zero ideal and factor it uniquely into prime. This has important connections to number theory. I'll motivate that a little bit next time, and then we'll show the equivalence of things. Any questions? Adam Price is speaking in the Math Club this week, and it sounds like a really interesting one. He's going to talk about geometry, so be there if you can. And answer, do you have any questions?